Early on, 16-meter dish antennas were built, and later a few 26-meter ones. They both shared the basic XY control. The reflector pivoted on a bearing in what we'll call the X-axis, and below, the reflector in X-axis drive would pivot on a bearing perpendicular in the Y-axis, allowing the reflector dish to cover the entire sky. The access drives were stacked vertically as shown. However, as the need for even larger reflector dishes became necessary as spacecraft were sent farther out, this design did not scale well, since the entire load would rest on the lower axis pivot point, and the increase in weight as the dish grows is nonlinear. Enter the azimuth and elevation approach. This allowed the heaviest moving assembly to be supported on a steel track, and allowed the construction of 34-meter dish antennas. The assembly would be supported on this axis via 4 large steel wheels running on a thick steel track, and only the dish would need to be supported on bearings for the elevation axis. For our 70-meter dish antenna, due to its extreme weight, estimated at over 7 million pounds, the wheels had to be replaced with floating pads, since even with steel wheels and tracks, the small concentrated contact points of wheels would have deformed under such loads. These pads spread the load out over a much larger footprint. However, since blocks of steel don't roll especially well, they needed to slide. To do this, a high-pressure hydraulic fluid is pushed under each block, allowing it to float a few millimeters above the runner. So the pad is not solid. It has a number of holes which allow fluid to be pushed under the pad, causing the pad to float, kind of like a puck on an air hockey game, but using fluid instead of air. The structure is kept centered on the azimuth runner with 3 pairs of rollers which ride on a center runner band. But because of the fluid, the pads run not only on the runner, but in a trough, keeping the fluid from being lost. Sweepers on both sides of each pad constantly suck up the fluid as it pushes out from under the pads, and returns it to the supply tank, filtered of course, where it is used again in a mostly closed system. A couple of improvements are being implemented in replacing the track, referred to as the runner. Originally the runner was 5 inches thick. The new one will be 7 inches. The material used to grout under the runner was compromised by years of hydraulic fluid being absorbed into it. The new grout is more impervious to fluid intrusion. To compensate for the thicker runner, the pads will be machined down 2 inches in height. Now, how do we get the weight of the antenna assembly off the runner so it can be removed and replaced? Enter what I call the maintenance support leg. When the 370-meter antennas were built, each site also built a structure that could hold up any one of the 3 corners at the pad location, so any needed repairs could be done in that location. All 3 of these were sent to Goldstone, so DSS 14's total reflector assembly could be held up completely off the runner. First, the outer runner wall, the 2 walls keeping the hydraulic fluid in, constitute what is called the reservoir. Hydraulic jacks were then placed on each side of each pad. A central controller was plumbed to each jack, and the pressure was increased until the whole 7 million plus pounds was lifted a few inches into the air. This allowed the 3 pads to be removed from the structure and then lowered to the ground. 3 huge brackets were then attached to the locations from which the pads were removed. Then the 3 support legs were attached, and the jacks lowered so that the structure was now being supported by the 3 legs. To improve access, the narrow catwalk around the antenna was enlarged using scaffolding. The old runner and support materials were removed from the antenna. In preparation for this effort, I was also involved in getting some of the replacement materials. The new runners are 22 feet long, 7 inches thick, and 44 inches wide. 11 specially made ingots were procured and sent to a machine shop to be machined. First for flatness and thickness, and then for more detailed shapes. However, before the heavy runners are put on the antenna, we need a very strong and precise surface on the antenna. To do this, a 1-inch thick plate called the sole plate is placed on the antenna and adjusted to be flat within a few thousandths of an inch all the way around its roughly 250-foot circumference. 22 of these were machined. To allow for fine adjustment as the antenna wears, between the sole plate and the runner are placed 360 fiberglass shims, which can be replaced with thicker or thinner ones down the years. Obviously, they must all start out within the same thickness.